still don't cover here, so it's pretty interesting for everyone, and it's also very useful for research and for industrial purposes also. So we are glad to receive to Professor Wei Xiong. I will read the biography of Professor Xiong for everyone that was not here yesterday. So Professor Xiong is the director of the Physical Metallurgy and Materials Design Laboratory at the University of Pittsburgh. Using CALFAT-based ICME methods, Professor Xiong works with materials design and process optimization, which covers a wide range of inorganic materials and focuses on phase equilibria and phase transformations. He has more than 70 publications related to physical metallurgy, including 7 invited book chapters. Professor Xiong serves on the ACM International Alloy Phase Diagrams Committee, the TMS Alloy Phase Committee, he's the chair, by the way, in the TMS High Temperature Alloys Committee, the TMS Additive Manufacturing Committee as well. He was the TMS ICME Education Subcommittee Chair, and he has received several academic awards, including the Best Paper Awards of the CALFAT Journal in the 2012 and also in the 2013, the TMS FME Young Leader Professional Development Award in the 2015, the Outstanding Reviewer Award in the 2020 of Acta Materialia, the CALFAT Young Leader Award in the 2020, and the TMS Early Career Faculty Fellow Award in the 2021, as well as the APDIC Best Paper Award in the 2021 and the National Science Foundation Career, this means Faculty Early Career Development Program Award in the 2021. Professor Xiong serves as an associate editor of the journal Science and Technology of Advanced Materials, and he serves also on the editorial advisory board of the journal Materials Characterization. So we are glad and honored to receive Professor Xiong today. So please clap him and please help me to welcome him to the talk.
Thank you very much. All right, so thank you again. First of all, I would like to check how many of you already attended yesterday's presentation. Can you raise up your hand? All right. Okay, thank you. So it seems like I need to duplicate some of the slides about the introduction. So this is a talk about additive manufacturing and the challenges related to microstructure engineering. And of course, I think it's a little bit disappointing to see all of these challenges. Therefore, I think it would be better to revise the title as opportunities. Once we have the challenges, we also raise up with our opportunities. I come from University of Pittsburgh. Once you're talking about Pittsburgh in the US, you know this is a kind of a city of steel. So US steel and all of the steel factories were producing this, and Carnegie Mellon, and of course they were founders of the steel production in the United States. So if you went to the University of Pittsburgh campus, we have the Cathedral of Learning. This is a landmark building of the University of Pittsburgh as well as the city. I think talking about Pittsburgh is a very old city, and also with the university is the oldest one of the oldest in the United States. As I said, you know, I happened to join university in 2016, and later I just find we have more than 150 years for the mechanical and material science. And certainly before that, we were doing metallurgy, and we are very small in material science right now. We only have 9 faculties doing this research. So it's a little bit tiny and focused on the alloys and hard materials. We're also expanding a little bit with the softer materials. So talking about research group, as I said, I joined since 2016. So our focus has 3 parts. The first part is based on the simultanea modeling, which I already covered yesterday with 2 talks. And we do quite a lot with the database development and computational materials design. However, we know material science is lack of data. Right now, a lot of people also asking questions about the AI and machine learning. So we focus pretty much also on how to extend this IC method based on some of the high throughput computation and experiment. And then based on that, we do a lot of design. So the design, including the new materials design, modify the existing materials. We also interested about advanced manufacturing, which certainly covers one of the topics we're talking about today is additive manufacturing. So If we look at the general design concept of additive manufacturing, we have to talk about processing, microstructure, property, performance, links chain, right? So we're going to list all of these microstructures. One of the fundamental and basic design of the additive manufacturing is making sure that you make a material which is comparable with the counterpart made by traditional manufacturing technique, or maybe even higher, right? So that's a case where once you introduce a microstructure with a received condition from the additive manufacturing, since this is a different processing, therefore you have to take care of a lot of processing optimization. You cannot use exactly the traditional manufacturing process with the heat treatment, for example. And surface finishing and everything has to be changed and accommodate with a as-printed microstructure. So that's a part we focus very much. And of course, we care about the composition design. As I said, if you design one of the alloys, maybe it's not necessarily suitable for additive manufacturing, even though it can be used for the casting or some other type of traditional process. So we focus on the composition. That's the most important part from the beginning. So for alloy additive manufacturing, I come from the community doing the hard material, alloys and steels and so on. We have different type of technique. I know that even though your university does not have the 3D printer so far, but if you look at your name of the university is UNAM. That's a short name of additive manufacturing with the last two words, right? So letters. So the additive manufacturing technique, first one has a selective laser melting process. I already mentioned a little bit. So this is based on the powder bed. Where you have one layer and then you melt the pattern of that layer designed by you with the geometry, and then layer by layer you can adding on top of that. Therefore you build a 3D structure. And then you can also have some type of manufacturing process like so-called directed energy deposition process, where you focus on having the powder spray or the wire spray. At the same time you are going to melt this part at the focal point. So the advantage of the first one is certainly you will be able to print some fine structures, all right? So the features of this macrostructure is actually much finer than this one, if it's wire or the powder. However, the advantage of these two is actually you can start to print different alloys at the same time. So typically you can use two wires simultaneously and fit into the one material. You control the feeding rate, and therefore you can start to print something so-called functionally gradient alloys or material. All right, so you can print alloy A to alloy B. And then this one as well. And another advantage is you can repair something, right? So if you already have this existing blade, for example, and you want to repair some of the parts, that's actually doable, right? Okay, so we're talking about microstructure in this lecture. So what is the difference, right? So if you check some of the printed microstructure of Ti 6.4, that's very commonly used for the Ti alloys. So the left-hand side is actually as printed microstructure from the laser powder bed fusion process. That's a building direction, all right? So you can see that all of these columnar structures start to show up, versus if you see the as-cast microstructure from the casting foundry, they actually not necessarily have strong texture like this. And then if you're going to do some of the further heat treatment, then you're going to see, oh, some of the heat treatment can remove some of the textures. So that tells us, first, the as-printed microstructure is different, okay? You have to customize with a suitable heat treatment in order to engineer the microstructure, making sure that you get desirable properties of the material. And then this is another comparison, it's similar. So since we're talking about heterogeneous material today, so I actually introduced heterogeneous microstructure. I think it's allowed. And you can see that it's actually heterogeneous with all of these 316 alloy and 718 alloys. Actually, if you do see some of the printed microstructure, you can see different directions will have different morphology of the microstructure, all right? Because the melting behavior at each point will be governed by the processing parameter, okay? You have a strong thermal gradient along the build direction, therefore you can see easier with this columnar structure. However, if you look at the another transverse plan, you probably don't see all of these melt pools. And of course, this also brings us a kind of another design area where you can change and modify all of these printing parameters to control the growth of the material with the initial point. And therefore, you can actually tailor some of the structure with the columnar, tailor some structure with the equiax. Then you can start to talking about heterogeneous grain. Okay, so that's one of the things we can look at some opportunities there. So this is the one that we did simulation and try to understand. For those of you who are not necessarily quite familiar with this thermal history, it's actually very much complicated because it's laser melting, depending on the heat source, of course. Some of the heat source can introduce heating and cooling rate up to 10 to 6 K per second, all right? So, and of course, depending on the material, depending on the powder that you're going to use. Anyways, I don't think anyone so far can precisely measure all of these thermal gradient at the moment, or temperature gradient at the moment. That is actually also bringing another challenge, where if you cannot measure it, it's very hard to improve and control. And a lot of things are still focus on the heuristic design of this microstructure. So what is the consequence if you have such a kind of heterogeneous developed with the texture? If you don't well design this, if you don't introduce some good heat treatment to tailor the structure, then you can see some of the structures will introduce a very strong anisotropic properties with the tensile strengths. And of course, you can test more with some magnetic properties and so on, all right? So, here is a question, right? So you have phase transformations, microstructure evolution. I think these two are almost identical concept. Then they're significantly different from the conventional manufacturing process. So how to perform microstructure engineering, how to modify phase behavior and grain structure. That's a kind of challenge, all right? With this, we want to further understand some of the basic design point, right? So if you're talking about the 3 stage of the design for additive manufacturing. Right now, you can buy a 3D printer that's not going to be very expensive if you want to print some polymers and plastic. That's just a kind of toy for the mock-up, right? And you can just design the geometry and print it out. And then if you want to have a prototype, that's actually a little bit harder, all right? So this is come from GE, as you can see, this landmark, this mark, trademark. However, this is not necessary to be the same size as you are going to take the flight. So this is still much, much more difficult than this one because you need to consider the integration of all different components. And then if you really need to go with something fly, that's way much difficult because you have to consider all the uncertainties, qualifications, and so on, right? And so that's the kind of level that we are discussing. We try to make sure some of printed structure to be useful. Right? So we look at this, the cost-effective design, then we also need to think about how the things relate to the hard material, alloys, and so on. So there are also 3 steps, right? So first, if cost is not a big issue, you have a lot of money, like Elon Musk, right? So he can directly use, he just wants to see the product and ship a lot of things to the space. And then you can just, choosing some of fantastic alloys and do the printing, right? So at the moment, but of course, he will also claim that he wants to reduce the cost because it's very important for the SpaceX. And then he will say, oh, I want to have some component with outstanding property and the low cost. And then these ones are actually allowing you to do some post-heat treatment. However, less is more, right? So the best thing to design a 3D printer or the 3D printed material is actually you want to have some good outstanding performance of the as printed alloy. And you actually don't need to design any post-heat treatment. You just use as received material to use that. That's the best, right? So you save a lot of cost and money, right? So that has to be done with a good understanding of all of these relationships introduced by the laser printing process, for example, okay? So yesterday I bring this picture and some of you already know, right? So I compare this with our human development, right? So with the feedstock material, is comparable with our human beings, right? So as I said, if you want to have a new baby, you don't want to drink, you don't want to smoke, right? So that's a high quality, right? So, and then you want to, send the baby to the good school, right? So, and then making sure that they can be educated well. So that's a part with additive manufacturing. So you want to really control a good laser melting parameter to making sure that you have a good melting design for this process. And of course, not necessarily everything can be designed well with the 3D printing itself. Therefore, you have to introduce post-processing, okay? So that's the part where similarly, you want to go to the universities. And then this university is based in Mexico, right? So, and in Hong Kong, you should go to Dr. Zhu's university. That's the best one, right? So that's the one you do the post-processing, post-heat treatment, all right? Okay, so talking about melting design, we have some case studies, all right? So I bring some of the studies from the literature, some studies from our own work publications. So if you're talking about this, there are a lot of innovations that you can make, all right? First of all, this is still kind of, the fundamental level. We are not talking about using this to, manufacturing process and making a car or a flight, because that requires a lot of qualifications and so on. But then, this is one of the studies published in Nature Communications. As you can see, people are actually not only using the melting process from the heat source, but also using some ultrasound to control the melt pool. Therefore, you have actually vibration happens during the melting. Through this, you can actually refine the grain structure as a received one, and you can see this is actually much refined if you think about the comparison with the typical one that you do without extra field with ultrasound. All right, so this is one possibilities that you can use, and actually some of the people also considering using magnetic field. That's actually also typical once you do a conventional melting with arc melt. All right, I still remember once I went to Chinese Academy of Science in Shenyang, and then they were using some magnetic field to making sure the homogeneity of the melting of the button alloys. That's actually also applicable. And the other thing is like, if you can understand quite well with the processing itself, then you also have a lot of opportunities to change directly during the melting process, okay? So that's one of the studies regarding the titanium alloy. If you look in detail, this is kind of, the sketch, however, is more or less the similar as you see the microstructure with the rear printing. So you can actually change all the thickness of the deposition layer in order to change the structure with the grains, okay? And then through this, you can introduce layer by layer structure, all right? So this is exactly the concept with the heterogeneous grain structure in the material. And through this, you can actually control the deposition rate, because the deposition rate, if it's high, then it does not allow enough time to have the growth happen. So it always limited with a nucleation and a very short time with growth. Therefore, you can refine the structure. Okay, that's a basic concept. All right, and of course, it's very hard to quantitatively doing some theoretical design for this. But then with 3D printing, you can do a lot of high throughput. Okay, this high throughput approach, you can actually change in the parameter easily with one printing. And you can use multiple processing parameter in order to see the response of the microstructure. So that's actually made us a lot of easier to control the parameters relation with the microstructure generation. And this is our work with, the Haynes 282. It's a very popular high temperature alloy used in different applications. So this is just showing an example. This technique is nothing different from the traditional welding, all right? So if you have a wire, you make an arc, and if you only weld one track, that's welding. If you be patient, you weld one layer, two layers, three layers, several layers, you start to do 3D printing, all right? So the same technique, all right? So that's the one we made some of the printing with a sequel. Sequel is a little bit difficult because you have to consider some of the multiple chalk on one layer. That's actually not easy to print. So we did this kind of printing. We just changed with a different melting pattern. As you can see, this is a single bead where you melt one time and coming back and go back and coming back. And then this is the meander, basically a zigzag. Okay, so that's two melting process. So what is sequence? What is sequence? And if you check with the cross section, you can see the single bead actually introduce a lot of fusion line. They are not necessarily parallel with each other, because the single bead is actually less with heat dissipation, okay? So therefore, you can, more with the heat dissipation, sorry. And then if you melt this direction, it's actually, you can wait enough long time to cool it down. Therefore, you can see a lot of melt pool shape here, okay? But then with the zigzag shape, it's actually very high intense with such a kind of cross section with the heat. Therefore, you can see some of the fusion line is actually horizontal. So with this, you can actually see some of the S-received microstructure difference, all right? So if you look at some of the processing, so this is a post-processing with the heat treatment. I just taking some examples, all right? So still connecting with Haynes alloy with some of the slides, okay? But then before that, I would like to say, you know, if you look at this Haynes 282 that I showed you, these grains are very large, okay? It's typically, if you look at the melt pool size is actually almost like 2 millimeter or even larger, okay? Because it's a traditional arc melting process. And then you would like to think about how to refine the grains, all right? So with this concept, we actually started with the Inconel 718. So this is the one that in the previous presentation talking about recrystallization. This is an old metallurgical concept, but it's still very useful with the new technique. So what we do with the Inconel 718 is also another high temperature alloy. So we compare with the cast and the LPBF, this is laser powder bed fusion process. And as you can see, this is as received microstructure with the cast. It's almost like a perfect equiax. With the LPBF method, you can see the columnar structure very much. However, if you can do well with the design of the homogenization, essential part of the post-heat treatment, as you can see, we put 1180 degrees C, 20 minutes, 1 hour, and 12 hours. And you can see the microstructure change, all right? With the LPBF, the 3D printed microstructure, you can see the grain size is actually finer and finer, all right? With the traditional ones, you just see some coarse grains, and you could sometimes some of the regions you can consider as abnormal grain growth, all right? So if you plot this, basically this one is the inverse pore figure is from EBSD. This is another GOR image that introduced from the EBSD analysis. All we can see is this plot shows you the residual stress indication, okay? We actually find the cast alloy does not have high residual stress as you compare with the printing process. So with the 3D printing, you can introduce a lot of residual stress in the beginning. So if the color is red and green or yellow, that's actually a high residual stress indication with a grain level residual stress, okay? Not forming the crack. And then if you dissipate with the stress at high temperature, as you can see, this stress helps you to refine the grains during the recrystallization process. And if you do an analysis with grain, then the additive manufacturing grains is actually become even less than the original one here, all right? That's a good indication. That means the additive manufacturing not always bring trouble if you can really define the post-heat treatment well, okay? That's encouraging. All right. So, this is not the whole story. We have a but, okay? If you look at the but, that's something bad, all right? Okay, why we say but? Because, as I said, every step is linked with each other. So, Inconel 718, that's actually a kind of precipitation strengthening material, right? With gamma prime and gamma double prime. So, if people design this, You have to making sure that you also need to do a very well design with the precipitation strengthening. Okay, if we blind ourselves and say, hey, I get a better grain, so the material would be better, that's actually not true. All right, because if you look at this, if you do the first homogenization process, you receive the fine grains. However, the consequent lower temperature aging process will introduce the different precipitation behavior. That is because the homogeneity of the niobium, which is the most important element in this alloy, contributing to the formation of gamma prime and gamma double prime, are actually different now. So you can no longer use the traditional cast alloy with a heat treatment. You have to further change the heat treatment schedule in order to ensure that you keep the same strength or even higher strength than the traditional material. That's the kind of piece of information we have to keep in mind. All right, so with this study, right, so we learn a little bit with the grain structure. That's very important, right? And then we further want to look at some of the even more challenging problem with Haynes 282. As I said, this is a laser powered beta fusion process. It's actually, the structure is much finer, all right? So if you do the wire feed process with Haynes 282, that's actually the wire feeding with the welding, okay? These columnar structures and so on, they are actually talking about even more than 1 millimeter, all right? You don't want this at all, right? So what we did is we check in with different temperature. We also want to promote some recrystallization process, okay? What we did is do different temperature, different time, all right? And of course, behind this, we were checking some segregations and use Thermocag and Calvert to predict some of the time which are the reasonable ones for the homogenization and guide us to do experiments. So that's the reason behind this choice of the temperature. I just don't discuss this here, all right? So after doing heat treatment, as you can see, some of the fine structures actually happens, but not so pronounced, okay? That's actually something that we think is still good, all right? So what we do is we check in with the SEM. As you can see, this confirms, all right? But another indication is you look at these two different printing strategy. You have the single bead, you have meander. Because the initial introduced microstructure is also different. Therefore, even if you can promote the recrystallization process, you are not necessarily guaranteed that this recrystallization will happen to help all the grain refinement introduced in this ANS 282. All right, so only happened with a single bead, have more pronounced. All right, not the full story. We have another but here. All right, so we do this. We further look at the grain structure, but then we also checked with as polished ones. As you can see, we see these dots here. These dots are actually, super saturated with some of the contrast and so on, just making sure that you can see. So we actually find if you do higher temperature with the recrystallization, then all of these pores are become a problem, okay? So if you have the additive manufacturing introduce microstructure as here, so you can see different pores, all right? But then if you further do the homogenization, these pores will start to grow. That means what? You have to use another technique to solve the problem. So you get refined structure, but you introduce more pores, all right? Because the pores is actually growing, all right? So what we need to do is actually introduce a heaping process. If you don't have heaping process, then hot isostatic pressing, then the pores will become another issue to retain the high strength for this alloy, all right? So Asian step, particularly, it can grow the pores. This is another example that you can find with aluminum alloys. So there are a lot of trade-off if you look at how to design additive manufacturing with all the heat treatment and processing, okay? And of course, you have a lot of degree of freedom to introduce a good design for the material as well, all right? So I don't want to, say all the things are bad and challenging about additive manufacturing. But I would like to still encourage everyone to use the traditional or classical metallurgical knowledge to design the additive manufacturing. So this is one of the studies that we checked before with one of the steers, all right? So if you look at some of the Martin-Cyclic transformation studies in the traditional publications, people were consider grain refinement with cyclic austenization process. This process is very simple, okay? So if you do a kind of casting and so on, you receive the microstructure, what you can do is you heat it up and let the microstructure to be homogenized and forming the austenite, and then you quench it and then start to forming martensite below the MS temperature. Therefore, you can do cyclic cooling and heating process. Once you form the new martensite, and then you will have more nucleation size, more dislocation density, and therefore you have much finer grain size. That's a kind of, the well-known technique with a cyclic austenization process. So what we did is with this new margin steer that we designed with a kind of try to commercialize it, is the composition, which is still quite different with traditional margin steer, 74 pH. So this is kind of information where you'll be able to see some of the Martin-Cyclic structure. And then we did additive manufacturing printing process. What we do, the post-heat treatment, is we use homogenization process, okay? So we do the water quench it, and heat it up, quench it, heat it up, all right? So what's the consequence? As you can see, this is the average grain size, so prior austenite grain size, all right? And then with one cycle, you get reduced, 2 cycle reduce, 3 cycle, because you have a limitation with the new nucleation size introduced by Martin-Cyclic transformation. Therefore, you reach with a plateau, okay? And of course, the hardness is also reaching almost the same at these cycles. That means within 3 cycles, you can actually refine the grains, okay? It's very, very encouraging story talking about traditional metallurgical concepts still can apply. And of course, another thing that we're talking about grain size with a refinement is using the thin opinion, grain boundary particles for the grain refinement. And Dinner was also, stayed in Pittsburgh while to develop his metallurgical theory. So for the thin opinion particle, basically this is from Wikipedia. I don't think it's a real picture, but then give you a kind of, the concept where if some of the particles, for example, in the steel, you have, the MC carbide particles, if it's small enough, close to, let's say, less than 50 nanometer, then you can have a kind of pinion jug once the boundary crossing this thin opinion particle. All right, so these one can actually delay the grain growth and making sure that you get a fine grain. And this is the same concept or similar concept if you do the casting. You introduce inoculation with the particles. All right, so this is kind of discovery type of work. We started with 3D printing of 316L. This is again is a laser powder bed fusion process. All right, so we ask people to hand down some powders, so we characterize it with a composition, and then this is a composition of the material. And as you can see, you have this oxygen content. All right, so we started with this homogenization again. We finished printing. We did high temperature processing with homogenization, 1200 degrees C. All right, austenize it. And then this is continuous with different examples. We did that printed one and with half an hour, 1 hour, and 2 hours. And visualize the picture of this IPF, you already see some of the grain effects, all right? It's actually a little bit finer. And as you can see, with the quantify, with the grain size is actually also get a reduction. And here, this is actually the hardness. I have the wrong index of the color, sorry about that. So, what is the reason behind this? So we check the microstructure. We look at the microstructure with EBSD, and then we also check with the TN. So once we went to the TN study, we checked all of these precipitations possible. So this is a printed one, initial, and we find a lot of the small dots, and it's also spherical shape, is happen tangled with the dislocation and the cellular boundaries. All right. So after 30 minutes, and we find some of the growth, and 1 hour, and 2 hours. And if you look at the shape is also changing. Starting from around between half an hour and 1 hour, it will become spherical to the rectangular shape. What's the reason? Okay, so we use Calvert, we use thermocalc, all right? So we calculate and understand better. So this is exactly yesterday, I was talking about iron chromium system, suspend sigma phase calculation or include sigma phase calculation. Okay, so we quantify, we did some yields in the STEM. And we identify these particles are actually spinel, okay, with manganese chrome, all right? And then we calculate. Wow, if you do the calculation, you see, I put the composition, use the iron database, including the oxygen content. I can see the spinel phase is actually showing up. And this is the perfectly, exactly the ideal size and the fraction of the thin opinion particle, all right? In addition, the thin particle has to be low, the fraction. If you have too much of the thin opinion particle, that will become an inclusion later, all right? So you really want to get this very low fraction of the spinel. But then we still did not explain the reason of spherical shape, all right? So what should we do? So we checked. Another one is rhodonite. It's the same type of chemistry, but the shape is just different. Okay, we further check with some information. We find rhodonite is actually a metastable precipitation oxide. So we were trying to understand. Well, we have the hypothesis is actually this is the relation of the Gibbs energy regarding the capillarity effects, the size effects. All right. So in the beginning, you have very small size of this oxide particle. All right, and rhodonite start to showing up with this interface energy. Therefore, it becomes equilibrium with gamma, with the austenite phase. All right. But after you do the annealing, the spinel start to show up. All right. So then you can see the gamma phase together with the spinel. All right. So how to confirm it from the Calvert calculations? You can easily do one calculation, just less than 5 minutes. All right. So what do? Suspend spinel. Because the Calvert database, we already have the rhodonite system, okay, in the system. Therefore, the rhodonite shows up exactly the same amount as spinel. Just confirms, all right? So that's a perfect explanation how you look at the structural refine connecting with these oxide particles at the thin opinion effects. All right, so with this, I would like to remind everyone, right? As I said, the step-by-step design is very critical for the additive manufacturing. So we studied quite a lot of different type of alloys and want to make it to be useful, all right? For example, yesterday I also talked about the high throughput uncertain quantification using machine learning to customize the high strength low alloy steel composition, right? So that's the same. I also mentioned even with the successful tensile test and Sharpie test with toughness. Behind us, we also did a lot of work with the post-heat treatment design. All right, because if you simply look at the homogenization for the AM alloy, they're actually showing different behavior during the homogenization. Okay, because the amount of bainite and martensite in the S-cast status is quite differently from the additive manufacturing. So you will no longer be able to use the traditional processing parameter to process the additive manufacturing component. That's very important, all right? So if you look at this, this is a casting example of the HSA. This is LPPF sample. And then as you can see, these grain structures, after you reconstructing with the prior austenite, is actually quite different from the cast example, all right? And of course, again, because this is a high energy density with additive manufacturing, laser powered battery fusion. Therefore, we actually get a good luck. We have some, good structure with prior austenite. You can actually get better with a metric structure. However, of course, consequently, if you do the design of the tempering to introduce some other particle strengthening with copper and so on, and also M2C carbide, then you have to change the parameter as well. All right? So, I talk about this. I discuss a little bit about this, right? So just show you some of the concept, how to introduce a design in the additive manufacturing. And this part is actually the ultimate chance that you can introduce some new material for the additive manufacturing, all right? So, here, some other, published work from the papers. And then as you can see, this is a kind of titanium alloy printed by wire-arc additive manufacturing. It's the same as we printed with the Haynes 282. It's a wire welding process, okay? The grain size is very big. They were using the same concept as xenon particle. So what they do is actually putting some tungsten particle into the material, because tungsten is very hard to melt, right? So therefore they act as a xenon particle in this and refine the grains, all right? And then particularly if you do the heat treatment, because tungsten particle is actually also resistant to the coarsening, therefore they can remain the small size of the particles, all right? So this is another attempt that they introduce some oxide particles to the titanium. So both are successful. I think quite a lot of people are actually doing this kind of work to refine the grain structures nowadays, all right? And then certainly this is a kind of modification, right? So you don't need to change a lot of things with the alloys, but you really can do some good design with a new composition, right? So this is one of the work published in another paper in Nature Communication. They were talking about introducing the new alloy, right? So Santa Barbara, they were working quite a lot with cobalt nickel alloys, right? So they were thinking about cobalt can increase the solver's temperature for the super alloy. So therefore, they changed the composition of the nickel alloy and introduced more cobalt into that, sorry. And then if you look at this, this is actually a much finer structure, and as well as the precipitation, they can reach the strengthening effects with L12 structure. Okay, but then we have to think about one problem, all right? So this is the same figure and same picture that I showed you yesterday, all right? What's the challenge? If you can get enough funding, you can test with a lot of alloy powders and so on. But then, even once we were studying this HSOA, right, so it's not easy, right? So we get the funding, we have the money, but we cannot get the powder, right? The cost is actually, tripled or even 10 times, right? So compared with the traditional stainless steel, right? So, and then remember, this high strength low alloy steel is actually commonly used in the Navy. It's not kind of strange alloy, all right? The lead-in time, right? So you send the money order to them and then say, oh, wait, now you have to wait for 3 months. Ultimately, we wait for 10 months, right? So that's a kind of, long time you have to wait, all right? And then they have to ask you to have minimum order quantity because you are the god, the only customer to order this powder, all right? So they will charge you more, all right? And then qualification, right? So how to control the composition of the powder. That's actually, one section that I introduced yesterday, right? So, but then it's very hard to control the composition. I checked with one of the vendors. They actually, is a Heterogeneous, right? So they were saying, oh, the oxygen content we can reach is this amount. We cannot make it lower, okay? Either you accept or not. Right? So that's no negotiation can be made, right? So with them. So that's a limitation with a lot of powder vendors, right? So we have to bypass this challenge, right? So, and of course, still, if you get a lot of funding, you can test, right? So one of our strategies is actually try to design some potential alloy with the prototype, which we can do some, the casting, arc melting, and checking some microstructure features. For example, if you want to design an alloy for additive manufacturing with a particle strengthening, you can do the test with a traditional arc melt, right? So get a sense, right? So if the phase stability is okay or not, right? But then we are actually coming through another kind of, the direction. So our group actually made a lot of efforts about like 5 years ago. Right, so because we got hurt by all of these issues. So what we do is additive manufacturing is not only an engineering technique, but it can also contribute to the scientific fundamental study. So one of the things that we tested is actually using the directed energy deposition technique, right? So these can allow you to print alloy 1, 100%, go to alloy B, 100%. If you have, multiple spray nozzles of the powder, you can study even, more materials together, right? So we have 2 nozzles, the twin nozzle, and we print 316L on the bottom and Inconel 718 on the top. And then we just do a very simple test with 25% increase. And very interesting. If you look at 75%, this is actually a fine structure. Very surprising to us, all right? So we were so encouraged by looking at this. And furthermore, as I said, everything comes with a story with, your previous experience. So we were thinking, how about do heat treatment further? Right, so we want to make sure after heat treatment, this material is still good. So we did the same thing, right? So we mixed with, 47%, 62%, 77%, just want to benchmark some of the studies, right? So we still use the same thing for the 718, 1180 degrees C, okay? Exactly the same time period, 20 minutes, 1 hour, and 2 hours. As you can see the microstructure, which one is finer? If you don't have any issues with color, you would agree with me. This is a very fine structure, okay? 1180 degrees C, 1 hour, you still can see very fine structure. That's very encouraging, okay? And this is a new material composition now, all right? So this is not the best of our study, all right? We already published this one, all right? So additive manufacturing letters, okay, so it's already published in this year. But then, with this concept, okay, we further utilize this material to process with laser powder bed fusion process. This is another one. So we were focusing on 75%, 77%. This is actually interesting. We just finished with one of the studies by one of our talent undergraduate students. And actually, it turns out with another technique, laser powder bed fusion process, focus on 77%, we still can get a much better performance, even compare with some of the original Inconel 718. That's actually exactly the same concept as Dr. Zhu were talking about, right? So because you want to get, the parent alloys generate the new alloy, the daughter alloy actually perform much higher than the average, okay, performance. That's a very nice concept, all right? So this is one that we actually received this HSA powder, right? Very expensive. Every day I was thinking about, okay, gosh, we finished the project, how to further save taxpayers' money, because I also pay the tax, and then further utilize this powder. Okay, so how about let's try to do some similar stuff as we did here, right? So we actually have 316L powder with HSA. And of course, that's actually not just kind of blind and press a button to do the printing, because the fundamental concept is HSA. Very easy to form martensite. Very easy, okay? And the 316L is very hard to form martensite. So if you think about the Stocking-Ford energy level, okay? Because this part is easy for martensite, this part is difficult for martensite, and then if we mix them together, in the middle, you will be possibly having a regime, you will introduce trip and trip effects. That's fascinating, right? No one studied this before, right? So I talk with the students and say, hey, how about we print one and check? And then another advantage of this technique is, this is a beautiful, beautiful technique to introduce high throughput experiments. Because with one printing, I can print so many compositions to evaluate the performance of different alloys. All right? That's a kind of mixture. All right, so what did we do? All right, so this is the bottom, this is top, and as you can see, 10%. 10% gradient is enough for my student working hard in the JPL, printed by a NASA printer. Okay, so he actually already, worked hard on this printing with different choices, finding 10% is more reasonable. Okay, so we get this alloy, and then we just introduce a very small strain, okay? So we introduce 6% strain. As you can see, if you study the trip and trip effects, you know that the best strain is actually very small to introduce fresh dislocation formation. And you would like to study some pair dislocations, even if you want to determine the stocking forward energy, right? So that's the part where we did a lot of, characterizations, EBSD. I don't know if I showed, I probably skipped that slide, and we did kind of mapping with the EBSD from the bottom to the top. And we find 40% is very interesting. This is 40%, and after deformation, and you can see the trunnion structure forms, okay? So you do see the trunnion structure. With 50%, we can also see the trunnion structure with martensitic transformation under the deformation. That's actually trip and trip effects. And why it happens is because you actually, during the melting process of the later melting, you actually can introduce some segregations, okay? With the segregations, some part actually, easier to form martensite, they form martensite. Some part did not have enough formation of the martensite, they keep as an austenite. And then the retained austenite actually have a little bit well-controlled with austenite stability. So after you press it, you start to form with the twinning and chip effects, forming with a new fresh martensite, okay? And of course, you can say this is fundamental, nothing new, right? But then we further print. So because we have our good collaborator at JPL, so they print quite a lot, right? So we say first print one gradient and then check individually, printing 40%. So we print 40%, okay? So what we are doing is, this is a single composition. This is a totally new alloy composition, 40%. And we do a kind of, the tensile test. As you can see, the elongation is actually quite good, and the UTS and the yield strength is also good, all right? So if you put this into the attribute plot, this is a fraction of the elongation, this is a UTS, and you can see this is a parent alloy, 316, okay? This is the HSA with the LPBF. We're actually, with the banana shape, we're actually pushing forward to this direction, okay? And you have to agree, this is also another type of heterogeneous structure, all right? So that is the reason why I give a presentation after Dr. Zhu, right? So I don't need to introduce how important of this kind of structure, all right? I have to say, I missed one slide here. So another encouraging of this new alloy is actually we don't have a very high elongation for this alloy, but we have very high UTS of this alloy. That means you can actually better to use this in the car structure materials and so on, because once you have a strong impact, you don't want to have the ductility too high, right? So if having the car crash, you don't want to press it too hard, right? So you want to still have low ductility, lower ductility, or maybe enough ductility, but then UTS, you can quickly reach the UTS. That's actually a high performance of these trip and trip effects, all right? So the take-home message, I would like to say, we have to take care of all the parts of the additive manufacturing. Coming from the beginning of the new material composition, and then you would like to take care of the melting and also consider a proper design of the heat treatment. An even more important concept that we have to keep in mind is once you do the computational design, it's not necessarily say, hey, I design one shoe ball for the printing. And of course, we have the models I also showed you. We have a copper-based ICE model to evaluate the cracking susceptibility, to making sure this alloy is good for printing. However, once you develop this kind of design with computational tools, you also would like to consider the heat treatment during that time, okay? So the design concept really have to cover all different stages of the additive manufacturing process, from the beginning to the end, all right? And of course, other challenging question could be, hey, how about oxidation? How about aqueous corrosion and so on, right? So these are usually not have sophisticated enough model to allow us to have quantitative design 100%. And of course, we still have to keep this in mind, okay? To identify correct microstructure features into the design of the computation. All right, so another take-home message again. So we're talking about these overlapping part, consider process and structure property performance. I think the most challenging one is how to identify the linkage between structure and properties, because we don't have enough model to say process into structure, but we have reason model to quantify it. But then this part is usually something missing between the collaborations of material scientists and mechanical engineering. Well, we have a lot of barriers talking about language and so on. All right. Another thing is, if you think about, some of the concept about less is more, right? So you really want to making sure that if you design super alloy, think about if I can print an alloy with a super melting process, simultaneously, you can also have the precipitation of the strengthening particle happens during the printing process. That's fantastic. Then you can minimize the post-heat treatment. That's one of the things that we actually also encouraged by studying this Haynes 282. Once we finish our printing, after checking with the TEM, we do see some of the precipitation happens with gamma prime. So that means there are some of the efforts that we can make for this kind of printing optimization process, okay? And then this indeed, one of the, published Nature work by Max Planck Institute, they will also utilize this concept to introduce the in situ precipitation of the particle, nickel titanium, into one of the steels, okay? So they can get very nice strengthened hardening effects of this precipitation right after the printing process. So you don't really need to introduce extra post-heat treatment. That's kind of one thing that I believe we need to collaborate between the material scientist, mechanical, and the manufacturing, all right? So can we use additive manufacturing to study some fundamental topics? So this is one thing that I already showed you, right? So with the gradient high throughput experiment. And then another thing is like, we have this laser powder bed fusion process. So this is different with this simultaneous melting, right? This one, you can only print one type of alloy, all right? But then, suddenly, one day, I received a bad news from one of my PhD students. He said, we bought a new furnace made in US, and then it's broken. We only use 3 times. And I say, okay, so bad luck. Should we dump it? No, we should save taxpayers' money. All right, so how should we do that, right? So this is the kind of tube furnace, all right? So we just keep this plug, okay? Close this part. And then we actually can do a printing with 3D printing. So we can print a long bar shape sample with this laser powder bed fusion process. And I put this long bar shape sample to here, okay? I heat it up, and then suddenly I can introduce a gradient temperature zone, okay? So I first do homogenization with this material. This is actually tested with 718 alloy. And then I can introduce a continuous temperature zone to study the aging process. So with one sample, you suddenly can study the precipitation strengthening at different temperature simultaneously. All right, that's perfect. So we validate this concept and we find actually this is 718, right? So after 15 hours, 616 degrees C, having the highest hardness. So nowadays, we are actually using this technique to further study a lot of strengthening effects of different material, including the Haynes 282, okay? So that's a kind of very nice concept that we can use for additive manufacturing process. It's a high throughput processing, okay? All right, so lastly, I would like to say, there are some challenges in the additive manufacturing, monitoring the temperature history and so on, right? So cooling and heating effects is very high, and then you have to better control all of this. And then the models and databases are critical, still very important. So additive manufacturing actually can help us to generate some useful data. And importantly, we need collaboration, mechanical engineering, manufacturing, and materials, all right? So like what I said, residual stress usually is very bad, right? So we can utilize it to do the requisitization process. But then residual stress, how to make a prediction? You talk with metallurgist, the answer is I don't know. All right. So you talk with mechanical engineering, Yes, I know, some of them, to predict some of the cracking initiation. But if you're talking about grain level of residual stress, no one knows, I think, all right? So that's a part is still blank, all right? I think there are some open questions and the opportunity for additive manufacturing. Level 1 is like, you know, what is a current picture of this, right? But then level 2 is how we can couple experiment simulation to effectively design this process and understanding the relationship. Level 3 will be how we can couple these modeling effects, okay, modeling efforts to make more effective design, and particularly for the location sensitive, because as I said, you know, if you print, the volume effects, location are all impact with the process and structure and property relationship. Level 4 is, you know, how can you accurately provide the feedback to control the processing, because you have to monitor, you have to measure, and then you can control the 3D printing process. And then level 5 is, you know, creating digital twin, all right? I think without these levels, digital twin probably is just a buzzword, all right? So we have to understand better in order to couple the digital twin. And certain fundamental level is, can we perform a reasonable simulation? A reasonable, not accurate, okay? Reasonable is good. Sometimes, you know, accuracy is very hard to reach, all right? But then at least you can show the correct physical picture of this process, okay? So, but then, can we integrate grain structure and phase stability, right? So as I said, Calvert has a lot of things talking about phase stability, but less strength with grain structure. But grain structure is very important for this design. Can we couple this? And then can we consider even the diffusionless and diffusional transformations in our modeling, all right? So that's important if you particularly design the steel, all right? So, and what are the existing models can be used for additive manufacturing? And what are we missing with the data? And then you can say that I have high confidence to approach to use machine learning process. Otherwise, again, garbage in, garbage out. You use very bad, low quality data. You never can have a very good quality of the prediction or the simulation. With that, I think I would like to, you know, appreciate all the work by my group members. And again, so I would like to also follow Dr. Zhu. If you are a good student, want to further approach to do the PhD study, welcome to connecting, and then send me the emails and so on. And we do have one student from Mexico. All right, thank you very much.
Thank you, Professor Xiong, for this excellent presentation. I would like to ask if there are some questions. You can ask in Spanish, in English, or you already know, in Chinese. So if you want to ask in Spanish, I can translate the questions for you. Do you have some questions? Yeah, please. Can you...
I'll ask in Spanish. Entiendo que hay muchas ventanas de oportunidades para la manufactura aditiva. ¿Hay alguna en la que podamos entrar para trabajar con usted?
Okay, thank you. I will translate the question for you. He understands, and I think we all understand, that there are a lot of future opportunities in terms of additive manufacturing. So the question of Charlie is, what is the best for working, going and work with you?
What is the best for us?
Yeah, for your group, yeah.
Yeah. So I think as I said, additive manufacturing we consider is a very good technique for engineering and fundamental study. So I think yesterday I talked about Calvert-based ICME. So I think a lot of people actually don't see the value of additive manufacturing producing a lot of useful data for the additive manufacturing fundamentals. So if you look at all the study that we're talking about additive manufacturing alloys, the microstructure features are very unique. All right, so a lot of design are actually using the traditional type of microstructure to design for additive manufacturing. That's actually low efficiency. So right now we want to do a little bit different. So we're actually using additive manufacturing as a kind of fundamental tool with the printing, and then we want to directly feed to the design process of additive manufacturing. This can be extended to the new materials. This is a very good example for the 75%, as I said. And then we call it using additive manufacturing to design for additive manufacturing. So there have, two good parts you have to balance. So I think, with the universities, we are limited with the applications, right? So you have to collaborate with the industry. But then this is part we can do much, much more, right? Yeah.
Thank you. More questions? Professor Gonzalo, please.
Thank you. Very nice presentation. Thank you very much,
Yeah.
Dr. Xiong. I have a question concerning the pores. You were talking about that the shape of the pores and their size change depending on the temperature. How do you can explain this? Which is the mechanism? I really don't understand how the pore can change. Yes, I was talking about the pores.
Pause.
Yes, you said that the pores change in their shape. They evolve from circles to the squares and so on. But how they can do that? Which is the mechanism?
Oh, that's a good question. Thank you. Yeah. So if you look at these pores, usually in the additive manufacturing ones, for these irregular shape of pores, we can see the lack of fusion. So actually, if you zoom in, if this is a laser powered bed fusion process based on the powder, sometimes you can really see some unmelted powder. Okay, and then this is a gas pore, which you probably introduce some evaporation of some materials, or maybe some of the shielding gas and trapped inside of the pores and so on. And then this is the big crack. But very interesting. So we actually, if we have to form a pore, and we only can make one choice, I would prefer to have a little bit closer to the regime of forming this gas pore. Okay, a little bit over melting. If you cannot, have a perfect melt, but I would like to introduce a little bit of over melt rather than lack of melting. The reason is because if you have this lack of fusion pores, no matter if you do heaping or what, because during the aging process, post-heat treatment, these pores will start to appear again, because you have this very small supermicron features still there, and then they can grow. But then with these gas pores and spherical shaped pores, after heaping process, it's a little bit better. So they will not reconnect with each other. So that's kind of the idea.
Thank you, Professor. I have one question. Whenever you design material computationally, are you thinking? Whenever you do the material design computationally, and you take into account the crack susceptibility of that alloy, do you take into account variables such as laser power, velocity, hatch distance, layer thickness of the process? And how do you get to that optimized process parameters whenever you do, for example, in selective laser melting? I don't know if you do like computationally or just try an error, and that's all.
Okay, that's a very good question. I think if you're talking with mechanical engineering people, okay, optimizing the processing of one existing material, so they would like to, have a lot of experimental testing, trials, and so on, combined with their simulations to evaluate the cracking susceptibility. Okay, they were going to understand how the residual stress were introduced such a kind of crack and so on. All right, so that's one type of efforts that you can predict the cracking, and I have to say they usually have to link with the experimental verification. It's very simple for all of our material scientists to understand some of the problem of mechanical finite element simulation. Because finite element simulation simulating residual stress, but then the usually very accurate residual stress has to be rely on the constitutive law. The constitutive law will be based on the material itself, right? So mechanical engineering not necessarily always capture the materials quite well, all right? And we know that different condition of different material will have different constitutive law, all right? So that's one level of accuracy that we cannot always capture, all right? So that's a cracking, okay, efforts with the simulation. The one that we use very often, based on our materials aspects, is actually we focus on the solidification process, okay? We have a model developed, coupled with Calvert ICME. I don't know if you were here yesterday, we have a small, showing up. There are several models that utilize for predicting the cracking of the material during the welding process. So we use shell simulation to predict this cracking susceptibility that can directly link in with the composition of the material through the Calvert ICME modeling. So that's the efforts. But then if you want to modify the processing parameters, we typically don't want to go with a design of experiments of all of these parameters, because you have hatch spacing, you have lasers, layer thickness, you have deep focal point, right? So you also have the beam size, you also have the velocity of the laser melting and everything, right? So that's too hard for us. It's a multi-dimensional optimization. It's impossible. So what we do is usually we just narrow it down. For example, one typical use is the energy density. People have one parameter. There is a function of all of these processing parameters. Guide us to link with this localized energy density versus porosity. So you can actually pin down several of the parameters, which is generally accepted, for example, for the steel, and you change some, maybe hatch spacing change a little bit, maybe layer thickness change a little bit, but based on these two changes, you can further optimize. I think that's the kind of, the decision where you have to make if you want to go find a kind of, the best parameter to do the melting, or you are actually also open with another chance. For example, later you do the post-heat treatment. For example, you can do the heaping process to further make the density to be high, right? So that's a kind of combination. I don't think anyone right now has a very sophisticated model that they can predict the cracking susceptibility. If they say yes, they're usually too extreme. They are too capable. Right?
Just one commercial, if you allow me. I'm working right now here in UNAM. I work with selective laser melting. Additive manufacturing is already in Mexico. It's in Gita Lab of manufacturing. It's here in Ciudad Universitaria. We are working there. The problem is that we don't work with the powder. We don't have like the technology to change that powder, but we have the technology to change the parameters. So that's why my question was for this way, that if we can change the parameters, then we can optimize. But I think it's the opposite that you do, that you design the material and it doesn't matter which process parameter is. But it's just a commercial. You're invited. We are at UNAM ICAT. If you want to work, or
Sure.
Probably I will be in contact with Liliana.
Yeah.
Thank you so much.
That would be nice. Yeah.
Thank you, Professor. Excellent
you.
presentation.
Thank you.
Congratulations. I have a question. You presented an equilibrium phase diagram to try to explain the presence of some particles. But I remember when I was doing some simulations to predict the presence of intermetallics in castings, in aluminum castings, I didn't use equilibrium simulations. I used out of the equilibrium simulations.
Yeah, sure.
So just curiosity, do you think correct to do it?
So this one is actually observed under the high temperature isothermal heat treatment. So we did actually 12 hours heat treatment at the fixed temperature. So I think, fixed temperature. This is isothermal.
I was confused.
Yeah.
Cooling rate.
Sure. So this is one that I think happened with 1200 degrees C. Yeah, with 2 hours and so.
And by the way, I couldn't be here yesterday to take the course on CalFat, and
sure.
I used, when I was doing my PhD, thermocalc. So can you tell us the differences, the advantages, disadvantages of both
Okay.
commercial package?
Sure. I think, I think both companies have a high quality of the software and database, but then they have some different focuses. For the thermocalc, they may have some focuses on some particular alloys which you have to really evaluate once you're talking with them, and then they have a lot of data bank information post online. So what I typically recommend is, if you are rich enough, you can buy 2 companies with both software and database. So if ideally, yes. Yeah, and then you should always look into the detail of the database information. For example, you may have copper database from thermocalc, the same copper database they claim from Panda or another company. But then you want to check all the subsystems with the binary and ternaries. And then if they are not included in the database assessment, then you should be aware of the quality of the prediction. So one of the ongoing NASA project we are studying was the wire arc alloy manufacturing of copper alloy on top of that we print the Inconel 625. These are become a high entropy alloy region, right? So we were checking the database with STEER database, nickel database, and HEA database.
ACSR.
Right, exactly. And then that makes them with high profit. They encrypted that database, right? So we are lucky with a little bit more freedom because I originally come with education of cover assessment. So sometimes we also do some ad hoc database in-house development. For example, we are not necessary to cover all the systems that we need to investigate. But then if we see some of the subsystems we need to have higher quality, we will go and visit that system, and then we develop by ourselves. And then we append that database, in-house database, into the commercial database. And then we can get a better prediction. And as I said, for the design, you cannot believe the models are always correct. No models are correct, right? So, but some model is useful. The cover-based ICME is just a useful model, where you still need to confirm with the experiment. And then I think a lot of alloy design related, you have an interest of understanding the alloying impact. So as long as the database sometimes can tells me, oh, if I increase the FCC stability, I want to increase more aluminum, or vice versa, then if the database can capture, that's actually fantastic, because you already save a lot of time with multi-dimension design, because typical alloy you're dealing with is actually more than 3 or 4, right? And then I can actually shrink in this design area and then just do some critical experiment. And then I can calibrate the model and make a better design. Yeah. Right, exactly. Yeah. Thank you. Yeah.
I ask me, if you don't mind, that I ask you a question more referring to the social aspect. May I? It's okay?
Social aspects. Oh, yeah, it's fine. Yeah.
Okay, I will ask in Spanish to make this faster. Bueno, él mencionó las impresoras 3D que funcionan con polímeros y como sabemos, pues estas han estado cada vez más fácil de conseguir para el público en general desde que salieron al mercado. Entonces mi pregunta es si este proceso de manufactura se supera el obstáculo del costo que mencionó hace rato, ¿qué soluciones hay o él propondría para regular su uso? Ajá, pero ¿qué soluciones habría para regular su uso? Para que, por ejemplo, una persona no pudiera imprimir sus propias armas, sus propias balas. Thank you.
Okay, Professor, we have a very interesting question for you.
Oh, okay.
Kind of difficult in social terms. The question is, how do you think that the products produced by additive manufacturing can be regulated somehow for the society to don't print things that are dangerous. For example, guns, for example.
Oh, okay.
Yeah.
I see. All right. Okay. So I never think about printing a gun, right? That's an interesting question. I think with the new technique, you always see the double side, right? So that's something that you cannot really control quite well by one single party, right? So, for example, this could be a similar questions go back to maybe 100 or 50 years ago, right? So people did a lot of quantum mechanics and now nuclear bomb and stuff, right? So how you should use all of this wisely, right? So the same thing happens with additive manufacturing. But then, these ones, I think, were related to policy making, right? So can you really digital all of the designs and process it well? Right. So, but then we should understand with additive manufacturing design, there are a lot of efforts right now, funding opportunities called cybersecurity. Right. So I couldn't speak too much about specifically about gun manufacturing and so on. That's actually too typical and too focused. But then a lot of funding opportunities are available for the cybersecurity. So if you print, can you well control the printing? Okay, if someone wants to attack, if they actually have extra remote control of your printing, that will become a problem, right? So then a lot of efforts have already been made. It's not just talking about material science or metallurgy. There are a lot of things related to IoT, Internet of Things, and control, manufacturing stuff, right? So that's actually like a kind of collaboration. People always want to extend a little bit as well. And also another thing is like, I also want to consider, like I consider maybe environment much more important, connecting with human beings, right? So for example, if you go to Hong Kong, maybe no one allowed to have guns, right? So is that correct, right? So then they don't have any issues, right? So they are very restricted of doing this. If in the United States, then that's a problem, of course. I don't know how to solve the problem, but then this could be a good question for the next United President's election, right? And then the environmental impact is also very important, related to our human beings, okay? Because thinking about if you print a small part, right? So you always need to, have some residual powder left over, right? How you should recycle these powders, right? After 10 times, you have all of this powder left. It's actually not easy to manufacture powder, but it's also not easy to recycle all of these powders. And talking about, if you do some of the powders with aluminum and so on, if it's very fine powder, it can be, toxic and even explosive. That's all the related issue to there, all right? So I think people have to be connected also thinking about how to making sure the effective design of the material and how to making sure that you, after you use, how can you recycle all of this material? This is also a question you can ask about to Elon Musk to design his car. After all of these electrical cars, you have a lot of batteries. Can you recycle all the batteries? All right? How we should do that, right? If all the batteries are here, right? So people always say, yeah, we can get it done if you give us money to do research and funding, right? So, but then I still see some of the problems, right? So I can't give you a perfect answer because I'm not ready to elect a United States president.
Thank you so much. So if you agree, Professor, because we have a small activity to do with the students, if you agree, we can finish here. And we can proceed with the activities, but first I would like to give a certificate of appreciation to Professor Xiong for this amazing talk. I will read the Metallurgical Engineering Department of the Chemistry College of the Universidad Nacional Autónoma de México appreciates Professor Wei Xiong for delivering the invited seminar Additive Manufacturing and its challenges related to microstructure engineering. Thank you so much, Professor. And we have also a very beautiful case with the name of Professor Xiong. Thank you. So we have a very fast activity with all of you. I think in the most of the students were in the first talk as well as in the second one. So I will invite to Professor Yun Tianchu if he can come in front, because Professor Yu and Professor Xiong, each of them will do a question, and if one student can reply in the correct way, the student will win the official T-shirt of the group. So, so who would like to start, Professor Yu or Professor Xiong?
Okay.
Okay, so please go ahead with your question, Professor Xiong.
So, you know, I did 3 lectures now, right? So, and then I think some of you attended all of these lectures. You probably have a reasonable good understanding about what we are doing regarding ICME, comfort, additive manufacturing, these processes. And I know a lot of students here. So after these lectures, you know, can you talk about, you know, what's your opinion? Except the gun manufacturing, all right? So what's your opinion, your vision about future of additive manufacturing, ICME, right? So, and then talking about some of the feelings, right? So this is one of the questions I think is an open question, right? So you can share some of the opinions from yourself. The question? I think
Yeah,
that's
sure,
a question.
sure. Who would like to give their opinion? You can raise a hand in Spanish or in English, and I can help you translate. Yeah, please.
Well, together with this material, the process, the geometry, additive manufacturing has many advantages. It is able to build complex shapes. So the next or the future, I think it will be focused also on the material, but also in the combination of lightweight structures such as lattice structures, topological structures. So these kind of structures in combination with the material, don't forget the material, are going to able like to lightweight structures and to send maybe have applications in aerospatial, in medicine, with these implants, titanium implants, even in defense. And I think that's going to be like the future, some applications like multifunctional 3D printing as well. And I think that's it.
Thank you. Yeah, I'm happy that, you know, you already understand all of the parts I was introducing about additive.
So now we have a second one, and the question will be from Professor Yu.
Okay, I'll give you an easy one. So, can anyone define what is heterogeneous materials? I think we used the 2 criteria there. Do you still remember?
Okay, please.
The definition.
Oh.
You took the note. That's great.
As in the definition of heterogeneous materials?
Yeah.
You are not allowed to Google it.
Yeah, no. No, I think I wrote definition, not the actual one. Sorry.
Oh, it's in your own word.
Yeah, think like materials that have been gone through the process of the heterogeneous dislocations, as in how could I say it? Yeah, I might have to read more on it. I am very sorry. Yeah, I don't have problem translating.
Anybody else?
¿No eran materiales que tenían diferentes resistencias en todos su, bueno, en el 100% de sus partes? Así.
So the answer is heterostructure materials are the materials that have different properties in different points of the material. Do you agree? Okay. Then, congratulations. So thank you so much. I think with this activity, we finish this very interesting series of seminars and courses. So I just would like to thank one more time to Professor Yun Tianyu and Professor Wei Xiong for their excellent talks. Thank you so much. Now we will invite everyone for a last coffee break. We have like some drinks. We have also a couple of biscuits. And we really hope that you learn a lot and that you enjoy a lot these activities. Thank you for your attendance. Good night. Good day.
Thank you. All right, so now I finish my task here.